So we're going to start this next chapter, which is chapter D, which is superposition of standing waves. And what we're going to talk about is oh, thanks. Okay. There we go. So we try that again. So we're going to talk about the superposition of standing waves. And we're going to talk about situations where, for instance, two waves occupy the same space and they can interfere with each other. So basically you get crest adding with crest, or trough adding with trough, or you get crest with a trough and trough with a crest. So we get constructive interference and destructive interference. And then we can get this because we have two sources of sound, like two speakers, where they interact, we get this interference effect. The other thing we can have is if we have reflection. So we have a source of sound and it goes out and then bounces back, and it's going this way and then bounces back. So that can cause us to have interference. And what we find there is that depending upon the geometry of the device, say a guitar string, and the speed of the energy traveling down the medium, in, say, a guitar string, and the frequency, well, what will happen is, depending upon the geometry and the speed, we'll find that we get what's called standing waves. These are the last waves left standing, if you like. They are just the right frequency to have just the right wavelength, that they reflect and interfere constructively. Whereas if you have the wrong frequency, then you have the wrong wavelength, and so you reflect back and interfere destructively, and you disappear. So when you pluck a guitar string, you're not plucking at 512 hertz, you're just putting energy in. And the reason why you hear 512 hertz is because the length of the string and the tautness of the spring gives a length and a velocity, which gives a wavelength which satisfies that 512 hertz frequency. So it goes on about an instrument such as a taut string or an organ pipe will support a family of waves that are harmonically related. It turns out if the geometry is just right for a 512 hertz wave, it's going to be just right for a 1024 hertz wave. And it's going to be just right for a 1536 hertz wave. Because if you're twice the frequency, you half the wavelength, and it's good enough for one wavelength, it's good enough for something that's half the wavelength. It's good enough for something that's 3 times the wavelength, typically. So there's going to be families. We call these harmonic families. And then two waves with slightly different frequencies will produce a sound that displays a thing called beats. And a beat is a modulation of the sound intensity. We think of it as a wave, and you know it's got some wave characteristics, but it's really a modulation of the sound intensity. So that's where we're going today. So let's talk about superposition of waves, and math. I wonder if I can get a blank piece of paper in here. Can I? Yes. Okay, because I want to do some scribbling. See, please wait a minute. Okay, so here's my thing. So I'm going to take somewhere, a pen would be nice. Oh, the pen doesn't show up. Well, that's interesting. So, so we have a speaker, and we have another speaker. This is going to be a bit bizarre. Let's see if I click on the black one, if it shows up. It doesn't show up. Isn't that weird? Okay, so here's my speaker, and I'm going to have to do this. This is kind of amazing. So there's the sound coming from one, and here's the sound coming from the other. And here's a point of interest, P. And here's another point of interest, P. And here's another point of interest, P. And the question is, will they hear exactly the same sound with the same intensity? And the answer is, it depends. They will not hear the same sound with the same intensity. And part of that is, well, they are different distances from the source. I'm sorry, this is, so that, those two path lengths are different. And so what we get is, we get a sound which begins from the bottom speaker, let's call it speaker 2 compared with speaker 1. A sound that comes from the bottom speaker will basically have further to travel. And so although they may be in phase with each other, they may be basically in sync. Because one of the speakers is further away from you, the sound is delayed in reaching you. Now this is going to be a continuous tone, so there's not going to be a quietness and then a sound. The tones are already taking place. So it's kind of a weird situation where the delay does not really matter. The fact that I'm farther away from one speaker than I am for another speaker does not really matter. What really matters is expressing that delay as a number of wavelengths. If the path difference is 0, then the crest arrives with the crest and the trough arrives with the trough. Or the compression arrives with the compression and the rarefaction with the rarefaction. And I get constructive interference, and so I hear a sound that's twice as loud as it would be from just one speaker. But if my path difference, if I'm a bit more over to the right-hand speaker than the left, so the path difference is half a wavelength. Whatever number of meters it is for this sound, that represents half a wavelength. Then the crest that arrives from one must arrive with something that's half a wavelength from a crest with the other. I'm going to try and draw this. If the path difference is half a wavelength, if that difference there is half a wavelength, then what is a crest arrives with a trough, because that's half a wavelength from each other. And so you end up with this situation where you get destructive interference. If I move a bit further, so now I'm a whole wavelength, however many meters that is, it's a whole wavelength for this sound. Then the crest that arrives from one does not arrive with the same crest that was produced at the same time. It's sibling crest. It arrives with, not its twin crest, it arrives with one that was produced earlier or later, but it's the next crest in line. But two crests arrive together. And so we get constructive interference. And if I move a little bit further, so now I'm 1.5 wavelengths apart, then, well, a crest will arrive with what? A trough. So there's this pattern that emerges, which is, if the path difference is a whole number of wavelengths, then we get constructive interference. And if the path difference is actually an odd half number of wavelengths, because a whole wavelength is 2 half wavelengths. So it can't just be half wavelengths. Odd half number of wavelengths, we get destructive interference, yes.
That's how the sound deadening on headphones.
So actually with headphones, what I believe is happening is that you got a microphone that's listening to the sound, and whenever it senses a pressure, a kind of a pressure wave, it tries to cause a rarefaction. It tries to oppose the sound that the effect that it's seeing.
So so it's not trying to use destructive interference.
It's trying to make constructive interference on the fly.
Okay, I understand. But pushing it away, or you mean?
It's trying to say, oh, you're a high pressure, I'm going to make you into a low pressure.
Okay.
So the two of them will sort of, oh, high and low cancels out.
Right.
Low and high, you're low, okay, I'll make a high one and you'll cancel out. So it requires very fast electronics. We couldn't do that 15 years ago because of electronics, I believe. Or not economically, let's put it that way. Okay. So the rules are, if the path difference is an odd half number of wavelengths, then we'll call it, then it will produce destructive interference. And for symmetry, let's say if the path difference is an even half number of wavelengths, then that will be constructive interference. Could I express that in terms of phase angles? Remember, again, sorry, this is, what am I doing here? So that's a wave, and there's my circular motion that goes with it. And I can say, well, the distance between there and there is one wavelength. And that's like going from there to there, which is like going from there round to there. So I can represent things in terms of wavelength, or I can represent them in terms of phase angles. So what's the rule in phase angle? If the phase difference, the phase angle, is pi radians, that's like half a wave, an odd half number of wave. If it's an odd number of pi radians, so if it's odd number of pi radians, I get destructive interference, and if it's an even number of pi radians, I get constructive interference. Now, the reason why we want to talk in terms of not just wavelengths but also phase angles, because if I wish to, I could talk in terms of these guys, and I could have speakers that are not in phase. I could say, oh, when one of them is pushing, the other one is pulling, so they're 90 degrees, well, not 90 degrees, they are half a wavelength out of phase. That's pi radians. We tend to talk in terms of the phase of the speakers in terms of radians. And so we either have to convert the radians of the speakers into wavelengths and add it to the path difference in wavelengths, or we convert the path difference into radians and add it to the phase angle between the speakers. So two ways of representing the same thing. I'm not too particularly keen on this, so let's see if I can. I don't even know how to get out of there. Presumably, up to the right. Lower right. There? That one? Save without editing. Save and exit without saving. Okay. So that's where we're going to. So let's talk a little bit about some math first. When two or more waves in the same linear medium, that just means that it adds linearly. 2 and 2 makes 4. The net displacement of the medium, that is the resultant wave, at any point equals the algebraic sum of the displacements caused by the individual wave. So basically, you're going to take this guy. Let's have a pen here. Let's take this guy, and we're going to add it to this guy, basically just algebraically, and we get that guy. Well, can we do that mathematically? So we say, well, y is equal to a sine kx minus omega t. Is that wave moving to the right or to the left? What is the symbol for its angular frequency? What's the symbol for its angular wave number? Okay. Not spring constant. Okay. How can I represent a wave which has the same amplitude, the same frequency, but has a slightly different starting phase? Oh, I put a little phase angle there. So this represents that guy, nice sine curve. This represents that guy, kind of like a displaced sine curve. We add them together. Y1 plus Y2 equals A sine kx minus omega t plus sine kx minus omega t plus phi. And of course you remember that sine A plus sine B equals 2 cosine A minus B over 2 sine A plus B over 2. Of course you remember that. I had to look it up in the back of the book, but that's okay. And so it gives me this answer. You're not responsible for any of this derivation. I just want you to be clear that you can do the math, and when you do the math you get a shape that looks like that. And what it did was it took basically that numerical value plus that numerical value equals that numerical value. Yes?
Sir, is this a destructive interference or a constructive?
Well, destructive and constructive are two extremes. This is what most of them are, which is somewhat in between. Okay? It's less than it could have been if you'd added the two of them together, but it's not completely cancelled out.
Oh.
So I would say it's mainly destructive. It looks like it's less than either one of these guys. So I would say there's been a diminution of the amplitude, so I'd say it's destructive. But it's a continuum rather than a... We tend to talk about the two extremes because it's easy to visualize. Okay, cool. Somewhere I have a... somewhere I have... I'm going to press on you. I wonder... See, I did that intuitively. So if we take the two extremes... If we have one wave like that and the other wave like that, and their crests line up and their troughs line up, then when we add them together we get this true constructive interference. It's beautiful. It's twice the amplitude. So you would hear loudness more than you would from one speaker. Not necessarily twice as loud because your ears are not linear. Remember that from Doppler effect, from decibel scale. If we have this where these are completely out of phase, then the crest arrives with a trough and the trough arrives with a crest, and we get 0. Now, we can easily show this with light. It turns out you can also show it with speakers. It's not perfect with speakers. We tend to get reflections off the room and everything, but you can definitely hear. I've done this. You definitely hear an increase and a decrease in the loudness of the sound between two speakers playing the same note. You can stand in one place and you can hear it loudness, and you step a little bit forward and you hear a quietness. It doesn't go to 0 in my experience, but it's somewhat quieter. But with light, it's kind of like it's beautiful. You can get total darkness or brightness, depending upon where you are in between the two light sources. Constructive and destructive interference. This is it in 2 dimensions. Okay, so we have a speaker here and a speaker there. And what I'm trying to show here, the blue is the crest. So here's, or if you like, a compression. So the blue is compression, and the green would be rarefaction. Or in light, you could say the blue is the crest and the green is the trough. But where you get points where the crest and the crest, or the compression and the compression, or the trough and the trough, or the rarefaction and the rarefaction, when you get similar things overlapping, you will tend to get constructive interference. So down the middle we get the trough with a trough, crest with a crest, trough with a trough, and you get constructive interference. There's a lot of waviness around here. If you were in a harbour and these waves were coming towards you, you'd feel waves that were twice as high as if you were at another point in the harbour. So this is a rough ride. But if you go a little bit to one side and you're at a point where there's a crest coincides with a trough and a trough coincides with a crest, they cancel each other out. So actually anywhere on this line there would tend to be some nice quietness. Anywhere on that line it would be nice and quiet, relatively calm. So I was going to show you 2 diagrams, one showing you the constructive interference and the other one showing you the destructive interference, but I did it all on one diagram. Yes?
When they cancel out, can we call it the destructive interference?
Yes, that would be
And that would be the purple one?
That would be the purple ones. That would be constructive interference. So 2 speakers are in phase. Listener A stands an equal distance from each speaker. What will she hear? Will she hear silence because it's destructive interference, loudness because it's constructive interference, silence because it's constructive interference, or loudness because it's destructive interference? So the two questions are, is it loudness or silence? And then, is it constructive or destructive that's causing it? So what do you think? You'd have loudness because basically no path difference. And the loudness is caused by constructive interference. So my path difference equals 0 meters. My path difference equals 0 lambda. My path difference is equal to 0 radians per second. And on all of those things, well, those two things tell you that you're going to get constructive interference. I'm looking at my path difference and saying, is it an even number of half wavelength, is it an odd number of half wavelengths, or is it an even number of pi radians or an odd number of pi radians? Oh, I think I just skipped one there. No, I didn't. Okay. Let's do something. Let's make this a bit more interesting. Do I have an eraser? Probably not. Maybe the back of my pen is an eraser. No, back of my pen is not an eraser. Okay. Let's say, just for the sake of it, let's say that this was 3.1 meters, and let's say this was 3.6 meters, and let's say that my wavelength equals 10 meters. So my path difference is equal to 3.6 minus 3.1, which equals 0.5 meters. Agreed? So that means that my path difference is equal to 0.5 over 10 meters, which equals 0.05. Actually, well, I can live with it. Let's live with it. Lambdas. Okay. So my path difference is equal to what would that be? That would be 0.05 pi radians. Agreed? No. 0.025 pi radians. Yeah. So is that constructive interference? It's not an even number of odd wavelengths or an even number of pi radians, so it's not constructive. If anything, it's nearly destructive. Can I change it? I just did I picked a bad number. I decided to live with it. Let's say that was 1 meter. So that was 1 meter. So that would be 0.5. And that would be, what would that be? 0.25 pi radians. No, it's 2 times 0.5, which is pi radians. 1 pi radians. Ah! It's 2 pi times a half, which is pi radians. So it's half a meter, and because my wavelength is 1 meter, it's a half over 1, which is half a wavelength. And because it's 2 pi radians to each wavelength, it's going to be a half times 2, which is 1 pi radians. So, based on the criteria of wavelengths, we are an odd number of half wavelengths. Agreed? We're 1 half wavelength, which is odd lambda, which is destructive. And based on the criteria of pi radians, we are an odd number of pi radians. So we're destructive. So in both cases, that will be destructive. That's a typical question. Okay, cool. So we say, well, okay, here we have a distance 1 and a distance 2 and a point of interest, and here's a source 1 and a source 2. And we say, suppose we have 2 sources of waves that are in phase. That means the speakers, they push when they push and they pull when they pull, and they do the same thing. And then let us assume that the waves from each source interfere at point P. So here's my point P. And the length for point P from source 1 is R1 and for source 2 is R2. At one extreme, if the difference in path length between those two guys is an even number of pi radians, then we can say, or it is a even number of half wavelengths, we can say it's constructive interference. If it is a odd number of half wavelengths or an odd number of pi radians, we call it destructive interference. If you want to figure out the number of radians, the phase angle, there's an equation for it, but you know how to do this. You take the path difference in meters and you divide it by the wavelength in meters. That gives you the number of half wavelengths. And then you multiply it by 2 pi. So this equation, you know how to do. We just did it. You don't need this equation. You know it. You know how to do it. So just watch out for learning equations just for the sake of learning equations. You know. So here's an example. So this is 2.8 and this is 2.2 meters. And the wavelength lambda is equal to 0.4 meters. Phase difference at P. So what's the phase difference? Well, my path difference is equal to 2.8 minus 2.2, which equals 0.6 meters. My number of wavelengths is equal to 0.6 over 0.4, which equals 1.5 wavelengths. So my phase difference is equal to 1.5 times 2 pi, which equals 3 pi radians. And just by the by, would that be constructive or destructive? If the two speakers are in phase, it would be destructive. Now, can I ask you, supposing that I started the two speakers out of phase, so there was a pi phase angle between them. Well, if I add it or subtract it, it makes no difference. I end up with an even number of pi radians, and so the whole effect goes to constructive interference. So we have this effect, and it's caused by the phase angle between the speakers and the phase angle of our path difference, and we add them together. And we ask ourselves, is it an even number of pi radians or an odd number of pi radians? This is just a reminder that one wavelength is 2 pi radians, which is 360 degrees. So a half a wavelength is 1 pi radians, which is 180 degrees. And just get used to that. We'll go backwards and forwards between the two. Interference due to path difference and a phase difference. So if the phase difference is pi, then we say if the total effect is an even number of half wavelengths, we get constructive. So now we're not saying the path difference. We're saying if the total effect is an even number, it's constructive. If the total effect is an odd number, it's destructive. So it's the same rule. It's just rather than talking about path difference, we're talking about the total effect, the phase difference between the speakers and the path difference. Yes?
So mathematically speaking, after we found the difference, in that first equation, if we had we would then add the phase, the phase difference between the two speakers afterwards.
Yes.
Okay, right.
Yes.
How do you figure out the total effect?
You just add. Take the phase difference of speakers plus path diff expressed as phase angle. That's the best way. Yeah. So you add them together. So consider the interference of two sound waves that are out of phase by pi radians. The path difference is 2.9 meters for that guy and 2.5 meters for that guy, and the wavelength of sound equals 0.4 meters. So I'm going to say path difference. I'm just going to start with my path difference. And I'm going to say my path difference is equal to 2.9 minus 2.5, which equals 0.4 meters. I'm going to say my number of wavelengths is equal to 0.4 over 0.4, which equals 1 wavelength, which equals 2 half-landers, by the way, 2 half-landers. My path, my number of radians is equal to 1 lambda times 2 pi, which equals 2 pi radians. My total effect is equal to my path difference plus my phase difference, which equals 2 pi plus pi, which equals 3 pi radians. 3 pi radians gives destructive interference.
It's for odd half pi, right?
No, odd number of pi. It's an odd half number of wavelengths, or an odd number of pi. Did I say that wrong before?
No, it's
It's just odd number of pi or an odd number of half wavelengths. Yep. Cool. Cool. Now, all right, so sound, yeah. But this occurs with light. So for fiber optic cables, this is really important for. Reflection of light, this is really important for. There's whole areas of technology that really, that really matters for. Yes?
so when they use this, when they're setting data through fiber optic cables, I guess you have to take into account these interferences that would change a 1 to a 0 or vice versa.
So yes, what happens is you have a fiber optic cable, say, and it's where you join them. Because you can't have a fiber optic cable that goes on forever, so at some point you have to join them.
Right.
And if you join them and you don't join them optically perfectly, if you have, say, you know, a junction and maybe it's got a slightly different refractive index, then what tends to happen is you get reflection and transmission. And the reflection, depending upon the optical properties of the fiber and the junction, the difference, depending on the optical properties, you will bounce back in phase or out of phase. And so it will interfere in different ways with the signal that's coming. And but typically the rule of thumb is if the refractive index, and we've not done refractive index yet, but if the refractive index of the medium you're entering is bigger than the medium that you're leaving. So from the front pane of a piece of glass, you get a phase jump of half a wavelength or pi radians upon reflection. But if you're reflecting from the back surface, where you're going from a high refractive index to a low refractive index, you get no such phase jump. So ideally what they do is they bond fiber optic cables with a medium which has the same refractive index as the fiber that they're using. So you can imagine the technology for that is quite sophisticated. They don't want, and the same thing actually goes with your coaxial cable. If you make like for cable TV, if you make a coaxial connector and you do it poorly, it will really mess with your signal. You really want it to be really zero impedance difference. And so there's a whole bunch of technology about that, and it all stems from these kind of ideas. We've only got a couple of minutes left, but we're going to talk a bit about standing waves. And again, we're going to have math. Here, there's my thing warning me there's 5 minutes to go. And again, we have this thing about this math thing. I wonder if I can do. Oh, that's an eraser. Isn't that interesting? So if I do U, and if I do, you just cannot see it. So if I have a guitar string, and I have a string that goes from one end to the other, there's certain things that have to happen. There has to be a node at one end and a node at the other, and that's the rule. But I can satisfy that in a whole bunch of ways. I could have a guitar string that bounces like that, or I could have a guitar string that bounces like that. All of those are allowed because there's a node at one end and a node at the other. And so you get these allowed wavelengths, which if you have a allowed wavelength and you have allowed velocity, you have a designated frequency. And so we'll see that there's a frequency for this first one, which is allowed. It is the one that will survive. We have a frequency for the second one, which is also allowed, and these two frequencies are harmonically related. And we have a frequency for the third one, which is harmonically related. So we get families of frequencies rather than one frequency on an oscillator like a guitar string. Same goes for organ pipes and the like. And our job next time is to learn how we can look at the geometry, the actual length of this string. And from that length and from our knowledge of these wave shapes, we can work out, and the velocity, we can work out what the allowed frequencies are and the pattern. That's what we'll do next time. And we'll pause it there. And what I'm going to do is